some examples. Okay, we're going to start with some qualitative examples, then we're going to look at some more quantitative ones. First of all, let me rewrite this, this impulse-momentum theorem in a slightly different version. This vector, instead of using this integral f dt in the integration, I can of course deduce an average force. Okay, so isn't it true that, by the way, this is external, isn't it true that, you know, the integral of a force or any quantity over a certain time equals the average value of this quantity or this force over the total time interval, right? F average, that's how we define F average, delta t. And that's the impulse, and that equals delta p, of course. In other words, F external, the average value of the external force equals delta p over delta t. That is another way of expressing the impulse-momentum theorem. Okay, so let's write this down. F average, the average force, right? Average external force exerted on the system equals delta p over delta t. Okay, in other words, the average rate of change of momentum over time. Let's take a look. Look at this example. A wine glass hitting the floor. You know, chances are it's going to break. If you don't want your wine glasses to break when it hits the floor, would you want the floor to be made of hardwood or with thick carpet? Common sense tells you that with a thick layer of carpet, the wine glass has a much better chance of survival. Right? Why is that? Well, let's take a look at this formula. You know, when the wine glass falls, right before it hits the floor, it's got a certain velocity going down, and the amount, which is the speed, of course, depends on where you drop it, right? Basically, it's in a free fall, right? Now, does it matter whether you drop to a thick carpet or drop it to hardwood? It doesn't matter. The speed right before the impact simply depends on where you drop it. Okay, did you drop it from 5 feet above the floor or 4 feet? That makes a difference. But whether the material of the floor is carpeted or hardwood, it doesn't make any difference. Okay, now after the impact, when everything is settled, the final speed, of course, is 0, right? It has stopped on the floor. So therefore, the initial momentum right before the impact and the final momentum after the impact, they are predetermined. Okay, they have nothing to do with whether the floor is carpeted or not. So delta p has the fixed magnitude, whether you're hitting the soft surface or hard surface. Now, what determines whether things are going to break? Well, that's the impact force, right? Say the glass, if a certain amount of newtons of force acts on it, it's going to break. Okay, so it's the force, the amount of force it receives that determines whether it's going to break or not. So what's that force equal to? Delta p over delta t. Again, the magnitude of delta p has nothing to do whether the thing is carpeted or not. So how come in one case it's easy to break, the other case it's not that easy to break? Yeah, as you probably have guessed correctly. It's delta t that matters here. Because the amount of force is not only dependent on delta p, which is the same in both cases, but also depends on delta t. So how would you increase the chance of the glass not being shattered? You want to decrease the amount of force, right? So how would you achieve that? Do you increase or decrease delta t? Well, of course you want to increase delta t so that this side is smaller, so you get a smaller impact force. This explains why the wine glass is not as likely to break when it hits the carpet, because it takes much longer time by comparison for the glass to stop when it hits a soft layer of carpet. It takes less time, far less time, for it to stop when it hits hardwood floor. So delta t is much shorter for the hardwood floor, making the impact force much greater, which is more likely going to make the glass break. Okay, so it's a simple application of this impulse-momentum theorem. Okay, similarly, what about automotive airbags? It's the same deal. Suppose in a crash, somebody was driving 65 miles per hour prior to the crash, and God forbid, that person hits a wall. And after hitting the wall, unfortunately, the car stops. Okay, so right before the impact, his momentum was equal to his mass times the initial speed, which is 75 miles per hour, whatever that is. And after the impact, the whole thing has stopped. So the final momentum is 0, right? So again, delta P is predetermined by your initial speed, by your mass, and by the final speed, which of course is 0. It does not matter whether the person hits an airbag or hits the steering wheel. It has nothing to do with that. Delta P is always the same. But again, whether the person gets severely injured or not depends on the force of impact. Okay? The force of impact. When the person hits an airbag, it takes much longer time for him to slow down and stop. So delta T is longer, and that is why for the same amount of momentum change, the force acting on the person is less, which is why he has a better chance of survival and a better chance of reducing injury. As a matter of fact, you can see from here, if delta T is 10 times as long, then the force of impact he receives is only 1/10 as much. This is how airbags can save lives. It is by prolonging the impact time. This is the trick they use, just like a wine glass hitting the floor. Okay, now let's look at something, another example that is a little bit more quantitative. And that is, why do birds and airplanes do not mix? Birds and airplanes do not make a good mix. Why? Because the airplane flies at high speed. I have here a picture of a jumbo jet moving at very high speed. Unfortunately, there's a bird in its way, and you know what happens. If this thing is very fast, the bird cannot quite get away from it, so there is an impact. Okay, don't ask me what happened to the bird, okay? I just want to know what happened to the airplane. If you're riding on the airplane, don't you want to make sure the airplane doesn't get damaged when there's a head-on collision? Okay, now, first of all, the bird is no match for the airplane when it comes to speed. The airplane flies a lot faster. So we can imagine for the moment that we can ignore the speed of the bird when compared to the speed of the airplane. And secondly, for simplicity, let us switch a reference frame so that instead of using the ground as a reference frame, we're using the airplane as a reference frame so that the airplane is at rest. Okay, so relative to the airplane, the bird is flying in. Okay, the airplane is not moving at all. The bird is flying in with a speed which basically equals to the cruising speed of the airplane. So let's call it V initial. Okay, the mass of the bird is small m. Small m. What is the momentum of the bird? Is m times V initial. And again, everything is measured from the airplane's point of view. That is the initial momentum. What's the final momentum? When the bird, makes a collision with the airplane and sticks on the windshield, well, relative to the airplane, the bird is no longer moving, right? It's dead, okay? So what's the final momentum? 0. Yeah, so what is the change in momentum? That would be final minus initial, so 0 minus whatever this value is, as far as the absolute value of the final momentum is, of the momentum change is concerned. What is delta P? Absolute value. Isn't that equal to m times V initial, right? That's mass times initial speed, because the final speed is 0. Okay. What is the impact force between the bird and the airplane? We know it's a pair of action and reaction. The bird gives a force to the airplane gives a force to the bird. So the question is, how much force does the airplane give to the bird to change its momentum by this much over a small time interval, delta T? You know the collision time is relatively short if it's a high-speed impact. Okay, so let's look at that force. Okay, so we have F equals the magnitude, okay, so delta P over delta T. I'm looking at the magnitude. Okay, so let's make an estimation, shall we? Reasonable estimation. Delta P is m times V initial. I'm not talking about massive bird, just a small, average sized bird. Let's say the bird only weighs half a pound, which is not much. Half a pound corresponds to a mass about 1/4 of a kilogram. Okay, so it's 1/4. I'm only roughly estimating here. 1/4 kilogram. Times the initial speed of the bird, according to the airplane, that basically is the cruising speed of the airplane. What is the cruising speed of the airplane? Well, let's see now. A typical jumbo jet these days, passenger jet, travels at subsonic speed. The speed of sound in air is about 330 meters per second. You're talking about subsonic speed, let's say 70–80% of the speed of sound. So as a good estimation, we're looking at something around, say, 280 meters per second. That is very high by common standards, 280 meters per second. Okay, you divide it by delta t. You know the time of impact is rather short. It certainly is far less than one tick-tock, right? Because of the extremely high speed of the impact. You can imagine the bird get pretty much stopped on the spot very quickly. How small it is, I don't really know, but let's estimate it, shall we? Let's say it's a fraction of a second, right? Why don't we use a 1/4 of a second? We cancel with that. You know, you give or take a factor of 2. It's not going to matter all that much. You will still get a correct order of magnitude. 1/4 of a second. Okay, see, 1/4 cancels. What do you have here? You get a force. 280 newtons. Okay, so how much is 280 newtons? Have any idea what a newton stands for? It's of course it's a meter per second squared times a kilogram, right? How does that translate to pounds? How does that translate to pounds? Well, let's do a little review here, okay? If something has a mass of 1 kilogram, okay, 1 kilogram, and it falls under the influence of gravity, what's the force on it? What's weight, W? Well, 1 kilogram, mg, m is a kilogram, g is about 10, actually 9.8, but about 10 meters per second. This is about 10 newtons. 1 times 10, right? About 10 newtons. But you know 1 kilogram of mass, if you weigh it on a scale, it's going to show you about 2.2 pounds. It's roughly about 2 pounds. Roughly. So what does that tell you? 2 pounds makes about 10 newtons. So each 5 newtons is about a pound. Okay, so what you do, you take that 280 and you divide this by 5, you get roughly the amount in Newton, 280 over 5 in pounds. You get about 56 pounds. Okay, let's be generous. Let's say only 50 pounds. But think about it. This bird weighs only half a pound. And yet, the force of impact he delivers on the front windshield of the airplane in the frontal collision is 50 pounds. That's 100 times its own weight. Now, don't forget, that bird being so small has a small footprint. Okay, so we're looking at a very small area, concentrated area, where 50 pounds of force is applied. And what's the problem with that? The problem is the front windshield might actually crack, or even worse, it might break. And if the front windshield breaks, remember who's sitting behind? Yes, the pilot and the co-pilot. Okay? And if something happens to them, we're all dead. Okay? So, what does that tell you? Birds and airplanes do not mix. Not only do airplanes pose danger to the birds, of course, that's obvious, but the birds, even a small one like this, can also pose great danger to an airplane. We have seen examples, we have seen incidents where the bird makes a collision with the airplane and bad things happen to both of them. This is the reason why the front windshield of these passenger jets are specially reinforced, because they have to withstand high amount of impact, so they cost a lot of money. Each window pane can cost over $10,000. Partly because they have to be specially reinforced. They're extremely strong to withstand that kind of impact. Of course, you see that's money well spent, because after all, we're only safe when the pilot is safe, right? Okay, let me ask you a question just incidentally. Suppose you sit here. You and I sit here. Actually, way back down there, right? Okay. What about this windshield? Do you think the airplane company spends a lot of money reinforcing those windshields as well? Do they spend $1,000 on each of them? Well, probably not. Okay, is it because they're cheap? Well, actually, there's a good reason why those windshields do not have to be that much reinforced as the front one. Because after all, remember, yeah, the bird is flying this way. Why? The airplane is moving that way. Right? The airplane doesn't move sideways. Okay, so even if in the very, very rare case when a bird comes in like this and hits that windshield where you sit behind, the airplane flies this way. The bird comes in from the side. The bird can only use its own flying speed instead of the flying speed of the airplane. The bird does not fly nearly as fast as the airplane. So therefore, the impact is far less, because we're looking at, maybe 10, 20 meters per second at most instead of 280 meters per second. So those windshields, it's not necessary to reinforce them as much as the front windshield, which has to withstand a direct impact. As a matter of fact, birds and airplanes, they have big problems if they're mixed together. So in the world's busiest airport, which is the O'Hare Airport in Chicago, which happens to be right next to a wild bird sanctuary, believe it or not. So a lot of birds flocking in that area. Authorities has reached this extraordinary decision, and they tried all kinds of things to scare away the birds because they don't want to mix with the airplanes. So what they did eventually, which actually turned out to be quite successful, was they trained a legion of falcons, falcons. They used these falcons to scare other birds away. So these falcons did a good job. They successfully turned these birds away so that they do not congregate near the airport to cause danger not only to themselves but also to the airplanes. Okay, you recall that one of the biggest reasons why we studied the concept of work and energy was that mechanical energy under the right circumstances can be conserved, right? What's the circumstance? All forces doing work must be conservative. And you know the conservation of mechanical energy played an important role in solving certain types of problems. In fact, the nice thing about any conservation law, such as conservation of mechanical energy, is that leads us directly from initial state to a final state. As long as you know for sure that energy is conserved, you don't have to know anything in between. That's the nice thing. You go directly from initial state to final state, equating E initial with E final. That was really nice. And as a parallel consideration, we also can have so-called conservation of linear momentum. That's the second conservation law that we learn. In fact, there will be 3 conservation laws after we're done with Physics 1A. We are studying the second one. Under the right circumstances, linear momentum can also be conserved, and that plays a central role in studying certain types of problems such as collision. Okay, so what does it take for linear momentum to be conserved? Well, we start with the Impulse-Momentum Theorem, I external equals delta P. If the linear momentum is conserved, that basically means it doesn't change, right? So what is delta P? Which is P final minus P initial. Well, it's 0 because P final equals P initial. And what does that take if you want delta P equal to 0? Yes, you want the external impulse to be equal to 0. So here we go. If I external equals 0, then it follows that delta P must also be equal to 0. In other words, P initial equals P final. This is what it takes for linear momentum to be conserved. This is, of course, called conservation of linear momentum. The principle of the conservation of linear momentum. What's the condition? The external impulse must be 0. Okay, and remember, impulse is the integral of force over time. And as a sufficient condition, if the external force itself is equal to 0, then of course the impulse delivered is also equal to 0. Okay, of course you can also have an up and down force, positive, negative, positive, negative. So the positive impulse can cancel with a negative impulse and nothing happens at the end. But we're going to focus on a simpler case, where the external force itself is equal to 0. So of course that's a guarantee that the external impulse delivered by that force is also equal to 0, which means you have conservation of linear momentum. Again, like I said, the greatest area of application is a collision process. Let's